Hello, I'm Tom.
And I'm Mia.
Welcome to the Adaptics podcast. You know, this is our series where we turn these really advanced ideas in artificial intelligence and robotics into, well, simple, clear explanations. I mean, we all know this field moves so fast, and a lot of the time it can feel pretty overwhelming. So our goal is just to create a space where anyone, and we mean anyone, can build their understanding at their own pace. Doesn't matter if you're just getting started or maybe you're exploring the broader world of intelligent systems. Let's dive in.
In this episode, we want to explore the tension between open and closed AI models, why this divide exists, how it shapes innovation, and what it means for the future of AGI.
It's the defining dilemma of this entire technological moment.
It really is.
We are watching the capability of artificial intelligence accelerate at an almost unbelievable pace. And this forces a fundamental, really high-stakes decision upon the major developers.
Which is what, exactly?
How much access to these frontier systems should they provide? The rapid emergence of these incredibly capable foundation models means that every single release strategy,
whether you lock it behind an API or show the code?
Exactly. Each choice has potentially global consequences.
Yeah.
And that's why this whole question of openness and what that word even means for AI has become so critical.
I think high stakes is the perfect term, because for you, our listener, whether you're a developer trying to build the next big thing or just someone trying to understand the regulations.
It all comes down to access.
Right. The strategy chosen by these big labs dictates your future relationship with this technology. You see new models popping up constantly, each one claiming better performance. And your first thought might be, this power has to be shared.
Of course, that's the natural impulse.
But the material we've been looking at really highlights the immense risks involved.
And that risk calculation, it changes almost daily.
It does. So our mission today is a bit complex. We need to cut through some of the confusion and clarify the terminology around what open even means in AI.
Because it often doesn't mean what you think it means.
Exactly. Then we need to weigh the reasons why the biggest labs are choosing to keep their systems closed, which usually comes down to safety.
And then on the other side, we have to look at the incredible innovation that's happening in the truly open ecosystem.
And finally, and this is probably the most critical part, we have to analyze how this whole debate just gets so much sharper when we start talking about systems that are approaching AGI, artificial general intelligence.
And the extreme risks that come with that kind of capability. For you, the developer, this isn't some abstract debate.
Not at all.
The choice between using an open weights model, say Meta's Llama, and a closed API model like GPT-4 isn't just about a performance gap. It's a fundamental choice.
A choice between what?
Between retaining full, decentralized control over your own work, your own applications, or locking yourself into a vendor's API forever.
Where you're trusting them to set the terms of use, the pricing,
and all the safety protocols. This one decision about access, it shapes the entire economics and security of the industry.
Okay, so let's start there. Let's unpack that terminology, because open source in the AI world has become, I think, a real nuance trap.
That's a great way to put it. It doesn't have the same meaning or the same promise of complete visibility that it did for traditional software.
You're talking about things like the Linux kernel or the Apache web server.
Exactly. In traditional software, fully open source meant you got everything you needed to inspect it, to modify it, and to reproduce the result from scratch.
But in AI, that's not really the case anymore.
No, because of the massive capital investment in training and the often proprietary nature of the data, we now have a critical distinction to make.
Which is?
The difference between fully open source and the much more common category we see today, which is open weights models.
And understanding that difference is key to the whole conversation.
It's foundational.
All right, so let's start with the ideal. In the context of a modern AI model, what does fully open source actually look like?
For a model to be truly open source, to give you real transparency and reproducibility, the developer has to release unrestricted public access to several distinct components. It's not just one file.
Okay, so what's on that list?
You need the model architecture, the trained weights, which are those billions of numerical values that are the model's learned knowledge. You need the inference code, the training code.
And the one that gets overlooked most often.
The highly detailed data information.
And when you say detailed data information, you mean much more than just a vague line like, we trained it on a big chunk of the internet.
Oh, far more. And this is where it gets really difficult. True open source requires transparency on data provenance.
Where did it actually come from?
Exactly. It means knowing the labeling procedures the specific pre-processing methods, a detailed list of all the training data, whether it was scraped publicly or licensed for a high cost.
Goal being
Complete transparency and reproducibility. The idea is that a skilled person or organization could, at least in theory, build a substantially equivalent system. We saw some of the earlier, smaller models like GPT-2 get closer to this level of transparency.
But the whole landscape has shifted since then, right? As the models got bigger and training became more proprietary, most of the models being called open today fall into that other category.
They fall into the open weights models category.
And which models are we talking about here? The big names.
These are the models that have really driven the recent explosion of community innovation. We're talking primarily about Meta's Llama series, Mistral's very efficient models, and specialized systems like DeepSeek R1.
And what are they doing differently?
These developers strategically make the trained weights publicly available, usually under very permissive licenses like MIT or Apache 2.0.
So you get the weights, which is like the model's numerical brain.
And that's the core advantage for the community.
Okay, so if I have the trained weights, I have the model's knowledge. That means I can run it on my own machine, I can fine-tune it, I can use it pretty freely. That sounds pretty open, doesn't it?
It gives you the engine, absolutely. But, and this is a crucial but, it doesn't give you the factory blueprints or the proprietary maintenance manual.
So even though I can run it and fine-tune it?
Which is great, and often at a very low compute cost for smaller versions. The developers are intentionally withholding several key proprietary components.
What are they holding back, and what does that stop an independent researcher from doing?
They're holding back the detailed training data sets, the specific pre-processing steps, and for efficiency, the specific code they use for hyperparameter optimization.
They're keeping the secret sauce.
The secret sauce for how the model learns so efficiently.
Let's make sure we're really clear on hyperparameters for anyone listening. What are they, and why is keeping them secret so significant?
Okay, so think of the model weights as the final, perfectly baked cake. That's the knowledge base. Hyperparameters are not the ingredients in the cake.
What are they then?
They're the thousands of tiny knobs and dials, the engineer sets before the baking even starts. They determine things like how many layers the model has, the exact math function used for optimization, the precise learning rate.
So all the little decisions that make the training process efficient.
Incredibly efficient. And that's the constraint. If I'm an independent researcher and I have the weights but not the hyperparameters,
Yeah.
I'm at a huge disadvantage.
Why is that?
Because if you get those hyperparameters wrong, if you turn the knobs incorrectly, you might waste millions of dollars of compute time just to get a much worse result.
So access to the optimized hyperparameters is what lets big labs train better models for less money.
Exactly. So if they withhold that, it drastically limits independent reproducibility, and it really limits the community's ability to improve the core training process itself.
And it also gets in the way of auditing for things like bias, which are often baked into how the data is processed.
Precisely. If you don't know how the data was filtered or labeled or weighted, if you don't have that provenance, it is nearly impossible for an independent third party to do a thorough, critical audit for ethical concerns or embedded biases.
So calling a model open weights is a very strategic choice.
It is. It balances the benefits of community engagement with protecting massive IP investments and, critically, avoiding full accountability for the source data.
You mentioned DeepSeek R1 earlier. That's a good example, right? They released the weights, but their huge data set of almost 10 trillion tokens is still a black box.
Correct. That lack of data visibility puts it firmly in the open weights category, not true open source. And then, of course, you have the far end of the spectrum,
The fully closed approach.
which is where you find the models that cost the most to train and represent the current frontier. GPT-3, GPT-4, Google's Gemini, Anthropic's Claude.
And how does access work for those?
It's mediated exclusively through an API, an application programming interface. You send it data, you get an output, but you have zero visibility into the underlying code, the architecture, the weights, anything.
A true black box.
A genuine black box. The user has no control over its inner workings. All control and all liability rests entirely with the original developer.
So we've established that the closed approach is restrictive, it limits outside research, and it concentrates a lot of power.
It does.
But despite those obvious downsides for the wider community, the labs that are training the absolute cutting-edge frontier models, they consistently default to this closed, API-only access. Why? What's the logic there?
There are really three main pillars that support this closed-by-default approach. The source material treats them as paramount: alignment and safety, product stability, and then intellectual property and commercial viability.
Okay, let's start with alignment and safety. When we're talking about these incredibly capable models that cost hundreds of millions of dollars to build, why is centralizing control seen as the only viable safety measure right now?
It really all comes down to control over safeguards and just how hard it is to patch a distributed system.
What do you mean by that?
Closed systems let developers ensure the model behaves exactly as they intended, especially when it comes to maintaining the complex safeguards they built to prevent misuse.
So preventing it from generating instructions for, say, a bioweapon or a cyber attack.
Exactly. Or generating hyper-realistic deepfakes.
And what's the risk if they were to open source a model that capable? Why can't the community just police itself?
The core issue is the irreversible loss of control. The moment a model is open sourced, any safeguards or guardrails the AI lab put in place can be trivially circumvented.
Just bypassed.
Easily. Malicious actors can jailbreak the model. Or even worse, they can fine-tune the core weights to intentionally strip out all the safety measures and amplify dangerous capabilities. They can essentially create a customized malign weapon.
And there's no way to prevent that once the weights are out there.
The sources are very clear on this. No methods currently exist to reliably prevent this from happening once the trained weights are public.
That's a powerful argument. It suggests that even if a developer spends billions making a model safe, a determined bad actor could undo all of that work in a weekend if they have the weights.
Correct. And beyond that, the developer also ensures product stability and predictable behavior.
How so?
If access is only through an API, the developer can update safety patches, they can refine the alignment, they can fix flaws instantly for every single user. The model's behavior can't be unpredictably changed by someone fine-tuning it outside of their control.
Which is impossible once the weights are distributed globally. You can't just recall them or force an update.
You can never pull them back. Then, beyond safety, there's a huge financial argument. We're talking about models that cost hundreds of millions, sometimes billions of dollars to train.
Right, involving proprietary data, years of work from top talent.
That investment has to be protected for commercial viability. If a company like OpenAI or Anthropic just released the full code and weights of a frontier model, they would instantly lose their competitive moat.
Their entire investment would become a commodity.
Immediately. A competitor could just stand up a nearly identical service without any of the original R&D costs. The financial incentive to stay closed is just immense.
Even just looking at the environmental cost.
Absolutely. Think about the carbon footprint alone. Training the original GPT-3 was estimated at around 500 tons of CO2 equivalent emissions. Llama 3's 8B model was estimated at 2,290 tons.
Protecting the return on that massive energy and capital spend is a huge priority.
It's paramount.
But this logic, this centralized control, even if it's necessary for safety and IP, it comes with really significant trade-offs, doesn't it? Especially for public accountability and research integrity.
Absolutely. The main trade-off is the limited transparency and oversight. When a model is fully closed, you have an intrinsic lack of transparency around the training data, the internal processes, how it even makes its decisions.
And that hinders any kind of external auditing.
Completely.
Yeah.
Independent researchers can't critically investigate things like systemic bias or discriminatory behavior or ethical concerns about where the data came from.
So we're essentially forced to take the developer's word for it. The very company with a commercial interest in claiming their model is safe and fair.
Which feels like a huge conflict of interest.
Yeah.
And it leads directly to the second major trade-off, the concentration of power.
How does that play out?
By restricting access, research becomes centralized and controlled. It forces the academic community and smaller developers to become reliant on a few dominant private companies.
And those companies get to dictate the terms of use, the safety rules.
And ultimately, the entire developmental trajectory of a technology that is quickly becoming central to our global infrastructure.
So it sounds like closed systems inherently consolidate political and economic power within a very small group of labs.
They do.
And that effectively slows down the broader democratization of AI development and expertise.
That's the core tension we're facing. The original goal of open sourcing was to distribute influence, but closed systems do the exact opposite. They make the really critical, expensive decisions made during training completely opaque. And that difficulty in getting wider participation is one of the biggest arguments against the closed approach.
So if the closed ecosystem is all about control and massive proprietary investment, then the open ecosystem is defined by distributed access and collective refinement.
Yes, and this is where the idea of the innovation commons really comes to life.
What exactly is the innovation commons?
It's the engine of the open ecosystem. It's a network where knowledge, resources, and tools are shared openly to foster collective innovation. And open foundation models contribute to this by becoming a kind of public infrastructure.
Which enables more competition and long-term economic benefits?
Exactly.
But I have to push back a little there. If the core architecture, the data provenance, and those secret hyperparameters are still held back, as we talked about with Llama and DeepSeek, how much of a commons is it really? Isn't Meta still fundamentally in control?
That is the core philosophical challenge, you're right. But the measurable impact on downstream innovation is just undeniable.
So even if the foundation is proprietary?
The availability of the trained weights unleashes what we call distributed integration progress, and we can actually quantify this explosion of community engagement using data from platforms like Hugging Face.
And those numbers are pretty staggering.
They really are. Since mid-2023, there's been a sharp linear increase in both the total number of users and new authors publishing models. Hugging Face has seen over 1 billion downloads of AI foundation models in just 2 years.
That shows an ecosystem that isn't just active, it's becoming exponentially more competitive and efficient.
Because new entrants don't have to start from absolute zero.
But what are these thousands of contributors actually doing? Are they building new Llama-level models from scratch, or is it something else?
It's primarily something else. They're focused on refining and customizing existing models.
Why not build new ones?
Because creating a truly competitive pre-trained frontier model from scratch, what we call the G or generalist developer role, is still prohibitively difficult. It requires superior proprietary data, huge hardware clusters, and specialized talent that's usually only available to big corporations.
So the open community excels at taking a powerful base model and optimizing it for specific real-world tasks.
Right. The open community drives that downstream application and refinement, the integration progress, at a speed the original lab just can't match on its own.
And this refinement isn't just marginal, is it?
Not at all. The data shows this synergistic effect very clearly. Fine-tuning models like the 7 billion parameter versions of Llama 1 and Mistral for specific tasks like code generation or complex reasoning has produced significant results.
How significant?
We're talking performance enhancements of up to 15% over the base model's original capabilities. That 15% improvement, driven by thousands of global, decentralized contributors, is what pushes the practical usefulness of the open ecosystem forward so quickly.
And it's not just fine-tuning. We're also seeing the rapid rise of other techniques, like model merging.
Model merging is fascinating. It lets users combine the strengths of multiple fine-tuned models. So you could take a model that's good at medical diagnostics and merge its weights with one that's good at creative writing.
And you get a third, specialized model that inherits the best traits of both.
Exactly, and all without having to do any resource-intensive new training.
The driving factor behind all of this adoption, both fine-tuning and merging, it has to be accessibility.
It's the foundation of everything. The vast majority, around 85% of all model downloads, are for smaller models, specifically those with fewer than 15 or 20 billion parameters.
And why is that?
Because accessibility is maximized. Users can run these models locally on their own computers or use cheap cloud resources like Google Colab. It means high-performance AI is becoming more and more decoupled from needing massive institutional computing power.
This brings us back to what we call the openness paradox. Open source seems to distribute integration progress very rapidly.
It gives users customization and local control.
Right, but does it really democratize frontier capability progress? Or does that power still sit with the original generalist developer?
And that's the catch. The effect of open source on democratizing influence over the frontier, the very bleeding edge of AI, is limited.
So even when they open source the weights, the original developers keep their competitive moat.
They do, through 3 main mechanisms: their proprietary data pipelines, their proprietary advanced training algorithms, those hyperparameter secrets, and the sheer scale of the compute infrastructure itself.
So the community can make Llama better, but they couldn't have built Llama 2 in the first place. They lack those 3 key ingredients.
Precisely. They're leveraging the massive multi-million-dollar investment made by Meta, and this actually creates a feedback loop that benefits the original developer.
How so?
The downstream innovations that are built on their architecture can easily be integrated back into the developer's future products. And the open source community effectively becomes a high-quality, pre-vetted hiring pool since they're already trained on the company's tools.
So open sourcing is a tool for democratization, but it simultaneously amplifies the influence of the original powerhouse developer.
That's the paradox.
This feels like the point where the debate shifts from market economics and innovation into one of critical global risk.
It does.
The tension between open and closed models gets so much sharper when we start considering systems that are highly capable foundation models, the ones that are approaching AGI-like capabilities.
Once these systems start to acquire capabilities that pose extreme risks, and by that we mean the potential for significant physical harm, catastrophic damage, or systemic disruption to key societal functions, the decision to open source them has to change fundamentally.
So developers and regulators have to recognize that some models will just be too risky to release with unrestricted access.
At least until we have robust global governance and safety mechanisms in place.
What specifically are these extreme risks? We're not just talking about bad customer service here.
No, we're talking about malicious actors leveraging these systems to scale their attacks and capabilities far beyond what any human could do.
For instance,
Highly capable AI systems could be used to aid the development of new biological and chemical weapons, potentially shortening the timeline and lowering the knowledge barrier for non-state actors.
or they could be used for cyber attacks.
Exactly. Mounting sophisticated, hyper-personalized cyber attacks against critical infrastructure, like power grids or financial systems.
The most alarming part of the material here for me was the concept of the offense-defense imbalance. Why does AI inherently favor the attacker?
For traditional software, open sourcing often helps the defense. Right. The community can find and fix bugs.
Right. Many eyes make all bugs shallow.
But for highly capable foundation models, the balance dramatically skews toward offense. And there are a few key reasons for that. First, as we already said, open sourcing lets malicious actors easily disable any safety safeguards. The moment the weights are public, all that security work is irrelevant.
And what else? How does it accelerate an attacker's capabilities?
Well, second, open models drastically increase the attacker's knowledge of possible exploits. A closed model forces an attacker to spend a ton of time and resources just poking the box to find weaknesses. An open model hands them the internal architecture on a platter.
So it accelerates the discovery of vulnerabilities.
Right. And third, researching effective safety fixes defensive work is comparatively slow and resource-intensive. And the fixes are often very hard to implement globally.
And the final reason ties back to that irreversibility of release.
Precisely. The fourth point is that propagation is a nightmare. Once a model is open-sourced, there are no takebacks if harms emerge. If you find a vulnerability, it's incredibly difficult to ensure that a safety patch is adopted effectively by all downstream users.
So malign, fine-tuned versions will just continue to exist and spread.
And because foundation models are so general purpose,
Yeah.
any flaws are widely distributed and can be easily exploited.
The source material had some pretty chilling real-world examples of this already happening, even with today's systems. The sophisticated scams, for example.
They're scaling up dramatically. We've seen these high-profile scams using generative AI, like the one where a major financial firm lost $35 million.
That was the one where they used AI voice cloning to impersonate an executive.
Yes. They used it to pose as a company executive to employees over multiple calls. The voice cloning provided that critical element of trust that made the fraud work.
And then you have influence operations, the ability to generate not just misinformation, but targeted, tailored narratives.
Yes. The potential for misuse there includes using multimodal models to create interactive deepfakes of political figures, or constructing detailed false histories to support geopolitical influence campaigns.
There was that one research experiment, CounterCloud.
That was a perfect illustration. The system autonomously identified political articles, generated counter-narratives that sounded journalistically credible, and then it built fake journalist profiles to create a veneer of authenticity and spread the tailored disinformation.
It just shows how open access lowers the barrier for really sophisticated, large-scale deception.
It makes you realize the difference between innovation and weaponization can sometimes just be a license agreement.
But the race for scale itself introduces another critical and often overlooked ethical issue, the carbon footprint.
This is a factor that really demands greater transparency and accountability. Trading these models uses a tremendous amount of energy. It's an ethical and sustainability issue, right alongside performance.
The estimated emissions for a single training run can be just staggering. You mentioned GPT-3 was 500 tons of CO2 equivalent. LaMDA was around 552 tons.
And just for context for our listeners, 500 metric tons of CO2 is roughly the amount of carbon that it would take over 23,000 mature trees an entire year to absorb.
For one training run?
For one single training run. And those numbers just balloon. The open weights model Llama 3, the 8 billion parameter version, despite being relatively efficient, was estimated at a substantial 2,290 tons of CO2 equivalent emissions for its training.
So this high energy cost means we have to prioritize energy-efficient architectures.
The environmental burden is heavy. It makes energy conservation and efficiency a vital part of responsible AI development, regardless of whether the model is open or closed.
Okay, so given these intense, irreversible risks that come with fully open sourcing the most powerful models, but also acknowledging that transparency and distribution are vital for innovation, how do we find the middle ground?
Right. If full openness is too risky, how can we still achieve the goals of distribution and accountability?
What's the solution?
The industry is starting to recognize that full open sourcing isn't the only path to transparency. The emergent solution is a set of strategies for what's called mediated access.
So non-open source sharing options.
Exactly. These are alternatives designed to capture the benefits of openness, but with significantly less risk of proliferation harm.
Let's start with how developers can feel confident that their model won't immediately be weaponized. That's staged release impact testing, right?
Yes, it's an incremental process. They release versions of a model over time, often behind a tightly controlled API. So a developer might release a 10 billion parameter model, then a 30 billion, then a 70 billion.
And each stage lets them observe how the model is used and misused.
More importantly, misused. It lets them study the social impacts and implement safety patches before releasing the next, more powerful version.
And that observational data is critical. If a developer has to implement a lot of new safety measures between stage 1 and stage 2,
that's a flashing red light.
It's a strong sign that a full open release would inevitably lead to malicious use, because once the model is open, all those safety measures could just be bypassed.
So staged release lets them build confidence before an open release,
assuming no major dangerous capabilities emerge. But there's a trade-off. This process can delay the benefits from reaching communities that could use them responsibly.
Another strategy is granting controlled access to trusted parties, which gets us to structured access and external audits.
Structured access means the access is mediated. It could be through a research API, where more flexible fine-tuning permissions are granted specifically to trusted third-party researchers and auditors.
Which lets them do the kind of bias analysis and ethical study they couldn't do with a totally closed black box. Right, without creating the full risks of a public weights release to everyone.
And who are these trusted auditors? What kind of work are they doing?
These are external actors, specialized government departments, private expert organizations, independent research centers, and they're tasked with evaluating the safety and security of these models before or right after a restricted release.
A major example of this was the Alignment Research Center, ARC, evaluating GPT-4 before it was released.
Exactly. They were specifically searching for dangerous capabilities and systemic security flaws.
And that evaluation relied heavily on red teaming. What does that actually entail in an AI context?
Red teaming is an evaluation method that stress tests models specifically to find out how and where safety concerns arise. The goal is to identify dangerous model properties, security flaws like prompt injection or jailbreaks, or potential misuse applications.
So you're giving the red team privileged access to try and break it.
You're letting them probe and test the model to elicit new and dangerous behavior, but typically without open sourcing the core code and weights. The focus is on finding the easiest, most effective way to abuse the system.
It seems like the industry is realizing that deciding on safety by yourself isn't enough. You need diverse perspectives.
Absolutely. The push is toward a diverse and comprehensive set of experts because different viewpoints ensure a broad spectrum of potential risks are identified.
And this is driving calls for mandatory auditing?
Yes, for large and potentially dangerous foundation models established by clear government regulation. That would prevent developers from only granting access to friendly auditors who might be less likely to expose inconvenient problems.
Beyond just controlled access, the sources suggest that distributing control over AI development means changing the very organizational structures of the labs themselves.
This is about democratizing AI governance. It's a recognition that open sourcing alone can't achieve democratization when the most powerful systems stay closed. So we need alternative measures to dissipate control away from a handful of unilateral decision makers.
Who might be incentivized only by profit.
Right.
So what are some concrete examples of these new structures?
One option is encouraging labs to incorporate as public benefit corporations, or PBCs. A PBC is a for-profit corporation, but it's legally intended to produce a public benefit and operate responsibly.
So it gives the corporation a legal basis to prioritize public safety over short-term shareholder profit.
Yes. Both Anthropic and Inflection AI, for example, have this structure.
What are some other options?
You could implement truly democratic structures, like public oversight boards made of independent experts and civil society leaders who have genuine veto power over high-risk deployment decisions.
And then there's the more provocative idea of a golden share.
A golden share is a nominal share with the power to outvote all other shares. It could be held by a trust that's governed by a representative committee, selected by a random sampling of the impacted population.
That sounds like the ultimate check on unilateral power.
It's an attempt to create genuine structural decentralization of control over these powerful systems. And finally, of course, there's the role of clear, systematic legislation.
Holding developers accountable for downstream impacts.
Exactly. Clear legislation is needed to hold the developers and controllers of these systems liable, particularly when misuse is enabled by a lack of proper oversight or inadequate safety testing.
And this regulation can't be developed in a vacuum?
No, it has to be developed through deliberative processes that involve everyone: developers, open source communities, academics, civil society. That's the only way to ensure the rules reflect diverse interests and guard against the risk of regulatory capture by the very industry they're supposed to govern.
So the decision between open and closed isn't just about philosophy or safety. It's also driven by market dynamics and geopolitical competition.
Heavily. Let's analyze the economic drivers. We can simplify the market into two types of players, right? Yes. You have the generalist developers, or G, who train the massive frontier foundation model like a GPT-4. And then you have the specialist developers, or D, who fine-tune those models and build customized downstream applications.
Like a specialized medical chatbot.
Exactly.
And what determines whether G, the original developer, keeps their model closed or makes it open weights?
It largely comes down to the initial performance of their model, which we can call alpha dollar. Generally, G will prefer a fully closed strategy when that initial performance is really high.
Why is that?
Because if the model is already good enough, the generalist developer can generate maximum revenue through subscriptions and licensing with their closed API.
Yeah.
They don't need the specialist improvements. They just lock in the revenue and protect their investment.
So if the initial model is great, they keep it closed. But how does regulation change that dynamic? Say, a rule that penalizes highly closed, high-capability models.
Regulation that raises the open source threshold, for instance, requiring component disclosure or imposing penalties for failing audits, can sometimes improve specialist innovation, alpha $1, and increase the specialist developer's utility.
So if the specialist gets more access, they can innovate faster.
It's essentially utility transfer. You're moving value from the closed system developer to the open ecosystem specialists.
But the sources also warn about the risk of overregulation. You can push too hard.
Absolutely. The modeling suggests that extreme combinations of penalties can cause the generalist developer, G, to decide the cost of compliance and the loss of their proprietary advantage is just too high.
And in that scenario, they might just withdraw from the market entirely.
And refuse to release the frontier model at all. That's the worst case outcome. A deadweight loss where no one gets any utility and the world misses out on a potentially beneficial technology. It's a very delicate balancing act.
Now let's pivot to geopolitics. There's a rising trend of efficiency-focused models that are starting to challenge the raw scale and dominance of the traditional US-based closed models.
This is a really significant global shift, and it's often driven by necessity. The release of models like DeepSeek R1, developed in China, has shown that breakthrough performance can be achieved not just through brute force scaling, but through architectural innovation.
It's challenging the assumption that only US labs with unlimited compute can reach frontier status.
And DeepSeek R1 really demonstrated a different path to capability, specifically through its architecture.
It's built on a mixture of experts, MOE architecture.
Right. Unlike a dense model where every single parameter is used for every task, MOE models use sparse activation. That means only certain specialized expert parts of the model are activated for specific inputs.
Which makes training and inference much more efficient.
Vastly more efficient. DeepSeek R1 has a really robust MMLU score of 90.8%, which is highly competitive, but with a staggeringly low carbon footprint.
The efficiency comparison is almost unbelievable. Its training was estimated at only 44 tons of CO2 equivalent.
And you contrast that 44 tons to the 2,290 tons for Llama 3's 8B model, or the 552 tons for PoleM.
So this dramatic innovation in efficiency was probably driven in part by things like chip export controls.
It seems likely. They had to find a way to get high performance without relying on endless supplies of the most powerful Western GPUs. And it demonstrates a viable alternative path to the frontier that emphasizes algorithmic efficiency over just raw scale.
Which suggests that geopolitical pressure to reduce reliance on massive compute might inadvertently be driving a global trend toward more efficient and potentially more accessible model architectures.
That's the hopeful conclusion, isn't it? Architectural innovation like MOE is crucial for reconciling performance, efficiency, and sustainability. It shows that high capability doesn't have to mean an environmentally unsustainable closed system approach.
So as we look to the future, what's the most likely outcome? Does everything become fully open or entirely closed?
The landscape is inevitably moving toward a hybrid future. This debate about access and governance will continue to shape global outcomes. But it's very unlikely we'll see a single strategy win out. The market is just too diverse.
So we'll see a blend of strategies.
I think so. The most powerful, potentially dangerous foundation models, the ones approaching AGI, will likely remain closed or use that structured mediated access we talked about, like research APIs.
All informed by rigorous risk assessments and governance.
Meanwhile, the vast majority of smaller, highly optimized models, especially those using MOE techniques and under 20 billion parameters, will likely remain highly open weights. They'll continue to fuel that incredible speed of downstream integration and customization we see in the open community.
So this means that release decisions for highly capable models can't be simple binary choices. They have to be based on a fine-grained understanding of what the release of each component weights, code, or data actually enables.
And how the risk of misuse compares to the benefit of community innovation. For the most capable models, the cost of control, in terms of stifled innovation, has to be carefully weighed against the benefits of preventing catastrophic misuse.
So transparency and accessibility are vital for beneficial AI.
But for AGI-level systems, that transparency has to be pursued through those structured access and governance mechanisms, rather than just throwing the weights over the wall and hoping for the best.
This has been a really comprehensive exploration of this open versus closed tension. We've clarified the technical difference between true open source and these strategic open weights models like Llama.
And we've seen why safety concerns and commercial investment push frontier labs towards closed systems like GPT-4.
And conversely, how the open ecosystem drives incredible refinement and accessibility for smaller models. And we've analyzed how the potential for misuse, especially with AGI, means we have to move beyond simple openness to explore structured access and external oversight.
The central argument really holds up. Openness is crucial for innovation and democratization, for fostering that massive community energy we see on platforms like Hugging Face. But for the most capable models approaching AGI, the severe risks of misuse and that offense-defense imbalance mean that full initial transparency may be just too dangerous.
Which is why alternatives like staged release, mandatory external audits, and robust governance are so critically important right now.
Exactly.
So here's a final provocative thought for you to consider. As we noted, the data shows that smaller models, especially those using efficient architectures like Mixture of Experts, are achieving performance comparable to much larger, more sophisticated ones.
And they're doing it with far greater efficiency, remembering DeepSeek R1's tiny carbon footprint.
Right. Does that rapid efficiency trend eventually force even the developers of the most guarded frontier models to become more open? Because the utility they gain from the community's refinement starts to outweigh the diminishing performance gap they can maintain by keeping their secrets closed.
It's a fascinating race, isn't it? A race between architectural innovation and proprietary control. If an open weights model can achieve 95% of the performance of a closed model at a fraction of the cost, that economic pressure on the generalist developer to open up will be immense. That tension between capability and accessibility will fundamentally define the next few years of AI competition and governance.
Thanks for listening to the AdaptX podcast. If you have any questions, feel free to reach out to us.